It is my great pleasure to introduce Professor John Leonard. He's the Samuel Collins Professor of Mechanical and Ocean Engineering at MIT in the Department of Mechanical Engineering. He's also a member of CSAIL, the Computer Science and Artificial Intelligence Laboratory. He got his bachelor's degree from UPenn in '87, his PhD in engineering science from the University of Oxford in '94. And so this is really a great honor to have John here at this series about SLAM, because he actually introduced the term in his PhD thesis. And originally, and John, please correct me if I get that story wrong that I told my students before. So you originally came up with the simultaneous mapping and localization, right? And so the abbreviation for this would be SMALL. Which I think your advisor, Hugh White, thought was not completely appropriate for one of the most difficult problems in robotics, and so he suggested just swap these around, and that's how we ended up with the expression SLAM.
That's
and
pretty much it.
Awesome, good. I'm glad I didn't tell anything wrong. So John's interests are in navigation and mapping for autonomous mobile robots and underwater vehicles. He's been the team leader for MIT's DARPA Open Challenge team and has also been in industry with self-driving vehicles at Toyota Research Institute. And even after he came back to MIT, now he's still involved there. John is also a fellow of IEEE and the American Association for the Advancement of Science. And he won a TRO Best Paper Award. So without further delay, so John, if you want to get started, please. And at the end of this, we'll have a gathered accumulated questions that we'll ask you.
Wonderful. Well, thank you, Michael. It's really a great honor to speak to this group. And I apologize, as usual, I have way too much because I would love to. I could speak for 3 hours at least on this topic, but I know that you've had some really amazing speakers already in this SLAM summer series, and so I thought if you'd indulge me, I'd do a little bit of sort of history, so sort of past, some present, and some thoughts on the future of SLAM. And so I run a group at MIT called the CSAIL Marine Robotics Group. This is some of my students. This was actually last July or August, I think, right when people were just coming out of their apartments, and so they're trying to spell out the letters here, CSAIL MRG. And I truly wish, I invite you all to come visit me if you're in Cambridge, if the timing works. I'm going to do something a little unconventional. I'm going to show you my lab. So let's see. So if actually I'll stop the screen share. So if and most of my lab is working from home or remotely. But if you were here, you'd see Sophia is an undergrad from Cornell who's visiting us. He's working on a swarm of robots. And Chad here is working hard away at non-Gaussian inference for SLAM. We had a paper normalizing flow ISAM in ICRA. And then if I could show you more, we have another lab space. My students were working on trying to improve the robustness of semantic SLAM. And so in some ways, we've kind of gone back to basics this year. It was partly inspired by COVID. Can we think of very simple scenarios that actually confound existing algorithms? And so, so I'll come back to that in a minute. So I kind of feel like, obviously, machine learning has dramatically impacted our field. But I do have a sense of kind of what's old is new again, and revisiting kind of the more historical formulation of SLAM in the context of semantic SLAM with modern machine learning methods, I think is an exciting area for the future. So let's see, so I'm gonna go back to sharing my screen, and definitely send questions on the chat if you want. And so the ambitious plan for this talk is, I really wanna make this a kind of personal talk about my research journey, SLAM, AUVs, and self-driving. And then to try to go back to some of the historical kind of origins of robot navigation and mapping. And a lot of the challenges that remain today were actually identified by early pioneers, such as Hans Marvick, Rodney Brooks, Rajesh Shatila. And I want to just give a little bit of a historical kind of view, and then talk about some of our current research in inference and representations. And I'm kind of borrowing the spatial AI term that Andrew Davison uses so effectively. To me, SLAM is about understanding the locations of objects in the world, and the ability to have knowing your position and knowing the positions of and identities of what's around you, I think is important, not just for navigation, but kind of building higher levels of intelligence in robots. And so, so let's see. So why don't I dive in with the personal research journey and my background. So as Michael said, UPenn undergrad, Oxford. In Oxford, you only have 3 years for the PhD. So I actually submitted my thesis in October of '90, and then went back for the graduation ceremony in '94. And that's officially my degree date. But I was able to join the Sea Grant AUV lab as a postdoc in 1991, working on the early versions of the Odyssey underwater vehicle with Jim Bellingham, who was just a tremendous mentor to me. And I joined the faculty in '96, and various sort of organizational changes and opportunities at MIT. I'm really thrilled to be part of the Computer Science AI lab, where I'm talking to you now from. You know, if you've watched any of the prior talks in this series, you know a lot about SLAM. Build a map, use that map to navigate various sensors and various representations, various inference and learning strategies. This is a result from my former student, Harder Johansson, from right around where I'm talking on the second floor of our CCL building for probably 8 years ago now, using a PR2 robot with a Kinect. And clearly there's a lot of understanding about how you do visual navigation and tremendous progress in the field. But I still believe there are some fundamental challenges and kind of a go back to basics kind of mindset, and then try to marry the old and the new. That's what we're trying to do. So if, and so coming to MIT 30 years ago, you know, there's a saying at MIT, IHTFP, you might look it up. For me, it's truly paradise. And really MIT is paradise because of the people. And I'm just so fortunate. So we've been targeted for underwater vehicles. When I did my thesis at Oxford, vision was still in its infancy, and we used sonar. But I didn't know much about the ocean or underwater. When I came to MIT, sonar made a lot of sense. And so over the years, we've been involved with many different types of vehicles: Odyssey vehicles, the hovering AUV from Bluefin, the Remus vehicles, autonomous kayaks that we built. And John Fulkerson was a postdoc with me, did a tremendous project with reacquiring objects underwater using kind of SLAM techniques. And so throughout that journey, we've kind of had the underwater application as a real motivator. So a lot of the way that I approach the SLAM problem is driven by the difficult constraints of underwater: very poor communications, very easy to lose your robot, typically a very sparse environment where you might not see a lot of features, or your sensor data might be very noisy. And my hypothesis has been that we could attack the fundamental issues of robot navigation with a broad applicability to various types of robots: space robots, self-driving cars, aerial vehicles. But that underwater it pushes you to question your assumptions. And if done properly, it might sort of motivate new lines of research that actually have a broader applicability. And so being a professor at MIT is like a gift. I've advised or co-advised 24 PhD students, all truly amazing. And if you know the SLAM field, you know names like Michael Bossa, Ed Olson, Ryan Eustace, who I co-advised with Hanumant Singh, just a tremendous. I think if you kind of could think of all of the PhD theses in SLAM and SLAM-related topics, just that tremendous community, you know. And I've had truly amazing postdocs. And you know, Paul Newman was my first postdoc. I mentioned John Fulkerson, certainly Michael and Morris and Paul and Liam, and Michael Benjamin is still here doing autonomy for marine vehicles. You know, it's being a professor may seem like a very challenging job, but if you look at the integral over time of the people you get to work with and the impact that they're going to generate in their careers, I really feel like the luckiest person in the world. And so now let's go back to the origins of robot navigation and mapping. And in fact, for me, I say that I'm still working on my PhD. And in fact, I recently found this little handbook. There are a bunch of books on like advice for the PhD, but this book kind of jumped out at me. It's a kind of UK perspective, you know, someone from England, and it informs my view of a PhD thesis. I had only 3 years and no graduate classes, sink or swim, define a problem and try to solve it. And this book has a lot of little great nuggets. But one thing it talks about is the importance of your relationship with your supervisor. And I was truly blessed to have to be one of the first 2 students, along with Alec Cameron, for Hugh Dorrant White, who joined Oxford in 1987, right when I was starting, 86, 87. And Hugh did his PhD at the Grass Lab at UPenn. And he was a force of nature and is a force of nature, but he's a little less involved in robotics these days. But it's hard to capture the sort of energy and enthusiasm and kind of almost like magical convergence that happened in the 1990s, the late 90s, in trying to make progress on the SLAM problem. And so one of the best conferences of my life was the International Symposium on Experimental Robotics in Sydney in March of 1999. And I met Juan Domingo Tardos in an elevator at the hotel. And it led to decade-long collaboration, thinking about data association and related topics, and Jose Nira, and then visiting MIT. And I encourage you to be part of the international research community, to get out there post-COVID, to meet people at conferences and make friends. So I'm going to tell you a little bit of like kind of my historical view of SLAM, and very much like informed by still thinking about solving my PhD thesis. So if I go back to like so if I started grad school in 87, what existed at that time? So I'm going to play a little video clip here from the BBC interviewing a very famous Carnegie Mellon professor, Hans Marvik. And so hopefully this will work out the audio.
Back in the 1970s, Moravec started what he thought would be a very simple task. He hit a problem.
There were things that, although they at first looked like they might be easier because human beings do them more easily, that in fact turned out to be heartbreakingly difficult. And those were things like looking at the world and seeing what objects there were in front of the camera that was connected to the computer, and moving around competently in the world, the typical robot tasks.
Each flash here represents 15 minutes of computing time.
I wish I had time to play the longer clip here from the show. Maybe you can find it online. This little clip is right after Hans saying that he predicts, by the year 2030, that enough computation will be available that the entire capacity of the human nervous system can be replicated in a computer. So Hans is pretty far out there in his kind of ambitions for AI. You can read his book, Mind Children. But there's no doubt he was a pioneer in this question of how can a robot navigate through the world. So this is the Stanford Cart, one of the most important early robots, along with Hilaire from France and Shaky from SRI. And Hans had a single camera that he moved along the linear stage to do a sort of pyramidal 9 position stereo camera. To process the data, it took 15 minutes. So he basically would move the robot, process for 15 minutes, move the robot. And Rodney Brooks was Hans Marvik's office mate at Stanford, ironically. And I think Rod helped out or looked on some of these experiments and said, there's got to be a better way. And one of the tragic things is doing his outdoor experiments. This is near the Stanford Observatory. The sun would move in the sky and the shadow positions would change during the time when the vision system made its computations. And so, but I love this word here, heartbreakingly difficult. And I think that even today with drones like Skydio and all the what Facebook has and what all the different kind of virtual reality based Connect Fusion, etc., Elastic Fusion, you might say, oh, of course, visual SLAM is solved. But I would argue that if you think about sparse environments, small amounts of objects, that these problems are still that heartbreakingly difficult. When I walk around my colleagues' labs, like we gave a first lab tour in a couple of years post-COVID, and I love my dear colleagues upstairs working on manipulation. They're using QR tags or APL tags on all the objects. I was at Woods Hole Oceanographic Institution, they're using April tags on objects for testing undersea manipulation. How can we get a more general competence to basically see what objects are in front of the robot and moving around competently the typical robot tasks? And so if I think about why is mobile robot navigation and mapping difficult, this kind of template has guided my entire career. I think about these different axes of difficulty, and to the right we have representation. Choosing a representation is absolutely critical in addressing any artificial intelligence problem, but specifically robot navigation and mapping, we have a lot of choices. You know, we can think about metric maps versus topological maps, dense versus sparse maps, maps with objects, as semantic SLAM, I believe, becomes more and more prominent in our investigations. And really, and then I collaborate with some biologists, Mike Hasselmo at Boston University. It turns out that navigation and positioning of an animal is actually critical in forming memories. And there's a whole dilemma between allocentric versus egocentric representations. How does an animal or a human represent things in the world versus just relative to egocentric coordinates? And through our collective time working on SLAM for these many decades, a whole variety of representations have been employed. And clearly there have been successes, and sometimes I want to do the sort of everything but the kitchen sink, where we just apply all of the representations at once and do the very best we can. But once you choose a representation, you have to, SLAM is a deceptively difficult inference problem. And so we have to do state estimation. How do we estimate the locations of features in the world in the robot trajectory, or potentially just the trajectory in a pose graph-based approach? We have to solve the data association problem. Which measurements correspond with features, or which poses that we might be currently occupied correspond to past poses with loop closing. And obviously machine learning is an incredible tool, and more learning is coming online. But in addition to developing representations and performing inference, as a roboticist, I believe very clearly in the importance of building systems and making them autonomous. I think we have to close the loop and couple perception to planning and control. And we need to develop techniques that can go from beyond just a demo in the lab to true deployment. And of course, some of those are engineering challenges, but I believe that there are some other, I believe there's sort of fundamental tools we've yet to create that will help us dramatically improve robustness and generality of our solutions. So I did see one question in the chat. If anybody, the chat's not showing up here. Anyway, so just jump in even audio if you have an important question, okay? But I'll plow onwards. And in this great little book, How to Get Your PhD, A Handbook for the Journey, one of the important things is reading papers. And they have this nice little graphic here. They talk about like, and obviously with Google Scholar and Archive and the tremendous size of the research communities that we're in today, you know, there's obviously a lot of papers out there. But if you think about, my advice for a PhD student is, if you think about this kind of bullseye picture where there's probably an inner circle of the roughly 5 papers that are really closest to what you're going to do, your contribution. A lot of times I think about a SLAM PhD thesis as making a unit step in one of the dimensions of one of these multi-axis kind of things. So try out a new representation, try out a new state estimation technique, try out a new technique for active planning where you couple back to, you know, sort of SLAM processes. And if I think for myself, like looking back in time, 30 plus years, what were those papers that really influenced me? I think some of the questions in those papers remain today extremely relevant. And so one of my heroes is Rodney Brooks. And Rod was a faculty member here for many years at MIT. He's an emeritus faculty member now. Rod wrote this wonderful paper in the mid-'80s, Aspects of Mobile Robot Visual Map Making. And this, just the abstract, that mobile robots sense their environment and receive error-laden readings. They try to move a certain distance and direction and do so only approximately. Rather than try to engineer away these problems, it may be possible and may be necessary to develop map making and navigation algorithms which explicitly represent these uncertainties, but still provide robust performance. To me, this is the kind of the birth of probabilistic robotics. Now, Rod personally took a different path right after this this series of papers, Rod developed the subsumption architecture and focused more on building layers of complexity to create robots, say like the iRobot Roomba vacuum cleaner. But even then, like back when vision was in such its infancy, you know, Rod, the key idea is to use a relational map, which is rubbery and stretchy, rather than trying to place observations in a I would insert rigid 2D coordinate frame. And so this idea of having a symbolic map representation with uncertainty that's kind of rubbery and stretchy and fixable. A couple of things in this paper that really jumped out at me taking a fresh look. So this is actually a photocopy. I think these are Hugh's handwriting on here. That one of the sort of first, the key 5 or so papers, Rod wrote, you know, these problems are far from solved. And certainly that was true in 1986. I sometimes feel, even today, these problems, this sort of spatial artificial intelligence, far from solved. I'll buy you a beer and try to convince you why it's still far from solved. And Rod had this great expression in this paper: much remains to be done to produce complete solutions. And I've always had this dream of apt-get install slam. So imagine you get a new laptop, apt-get install slam, you connect your laptop to the robot, and then off it goes. It just can understand what's where in the world. No need for motion capture systems. No need for APL tags. No needs for having like cameras on the ceiling to help your little manipulator experiment. I want robots that can sort of understand the world around them. Now, if I look at the other choices for so let's focus on representation. So Rod talks about a rubbery and stretchy topological kind of representation. In some ways, this is one of the first references in the literature to the loop closing problem. And the idea that you don't need to necessarily have a rigid coordinate frame if you can just recognize when you're back where you need to be. An alternate view, which came out of Marvick's work, and Marvick obviously was pursuing an object-based representation of the world in the 70s, but working with Alberto Alfez at CMU, proposed the occupancy grid representation. And I've only met Hans once, but I do want to take this moment to sort of offer a tribute to Alberto Alfez. You know, we lost another giant in the sort of early, you know, pioneers in mobile robot navigation. Alberto did pass away just over a year ago this month. And Alberto was, with Hans, developed this representation where you could take sensor readings and sort of project them back into a grid map. And I think that part of the allure of this was sonar data was very noisy, and objects, you can look at this lab picture, like it's a pretty complicated scene with the bookcase and the file cabinets and so forth. And so it's appealing to think about a representation where you sort of back project your sensor data and try to use sort of aggregation of many measurements to overcome some of the challenges. And I think occupancy grid's kind of a precursor to things like TSDF and dense methods. Again, maybe a little before their time. But personally, at least as a grad student, I had a real anathema to occupancy grids, because to me, I think of handling sensor measurements as almost like a sort of a hand-to-hand combat with the data. Can I trust this one? Can I trust that one? What does this one mean? And if you just pour all of your data into a dense map representation, if there's too much uncertainty in that, you're not going to be able to distill meaning, and the errors are going to accumulate. So if I say, like, for my core sweet spot of papers, the one that was closest to my heart and my sort of more of a European school maybe was actually Rajesh Shatila's work with the Hilaire robot in Toulouse. I've got a wonderful collection of historical robot videos. This is from French television in 1982. This is in Toulouse, France, where the 2004 Slam Summer School was held. And one of the earliest mobile robots that could autonomously navigate using path planning, obviously a simplified world with the plywood models. And there's a great part here of Raja talking at the blackboard. I probably don't have time, but I want you to see young Raja.
Alors voilà comment se présente la scène. Nous avons une pièce dans laquelle il y a des obstacles. J'en dessine quelques-uns. Ces obstacles sont de forme absolument quelconque. Vous voyez donc qu'il y a des endroits où le robot ne peut pas passer, par exemple, entre cet obstacle et le mur. Une fois que l'ordre est donné au robot d'aller au point but ici, le robot se trouvant en ce point initialement, il effectue à l'aide d'un télémètre laser une exploration complète de l'espace, ce qui lui permet de constater.
Okay, I don't speak French, je ne parle pas français, but this school of thinking is that we should try to care about uncertainty and geometry and try to do consistent world modeling by fusing the sensor observations from multiple positions, taking local views and piecing them together. And in fact, the first complete SLAM implementation it deserves much more credit than it gets. And I think that's because the PhD thesis was written in French. Someone should translate this thesis, but Philippe Moutalier's thesis with Raja used laser scanner data to solve the sort of the common filter based, pose the common filter based problem, and in particular representing the error correlations in a consistent way so that you could get good error bounds and leading to good data association. So a little bit more on that in a second. So in my own life, another key influence obviously were Hugh White's papers. So Hugh had just finished his thesis on consistent integration and propagation of disparate sensor observations. We've got some objects. We want to sort of combine the sensor data to get the sort of geometric relationships between them. You know, I was a grad student in the basement of the lab called the Jenkin building at Oxford. We had this little box next to me is a data cube, which was a computer vision processing box. It cost a lot of money. I think it was either 60,000 British pounds or 60,000 US dollars. But all it could do was grab frame images from a camera and do something approximating canny edge detection at about 3 frames per second. So in the early days of my thesis, I was actually trying to fuse vision and ultrasonic ranging. I spent a couple months trying to get the data cube processor to just do simple edge detection so that I could extract features to do some geometric reasoning. And a little story, I was at Jesus College in Oxford, and after my first trimester, the sort of 3 semesters after the the Michaelmas term at Oxford, Hugh wrote a report to my college saying, I am completely dissatisfied with both the quality and the quantity of John's work. And it was a bit tough because I'd only been a student for a few months. You know, was rowing and trying to play rugby and various kind of enjoy life kind of things. But the reality was that computer vision was just too hard. And so I turned away from vision, and I used sonar. And so now at the same time, just around then, and we kind of independently pursued some of the same ideas, but giving sort of credit in the literature and then kind of figuring out what was out there. Smith, Self, and Cheeseman posed the stochastic map for spatial relationships. And effectively this idea of incrementally building a map using Gaussians to represent uncertainty and revising the map as you go. So this stochastic mapping process. Now, Smith, Self, and Cheeseman wrote a few really influential papers. They didn't really produce a compelling implementation, but they kind of mapped out this sort of the machinery of combining information in this kind of feature-based worldview. Very influential for me was Tracking and Data Association from Barcelona and Fortman. This book came out right when I was a first-year student. And obviously, Kalman filtering is a tool, but I think an important insight is coupling Kalman filtering with data association to try to associate measurements to different types of features in the world. And so we developed a sort of common filter-based framework for either localization or mapping and trying to put that together. And so, but our goal was to have, this is a sort of screen capture from a replay of a robot driving around in the basement of that building using sonar measurements that are predicted from a map and matched to the map, validated with validation gates. And the triangle is the dead reckoning, which kind of drifts off course. The best implementation I produced, the robot could navigate around the building for a few different, maybe about a few hours in a row, just kind of run the battery down and maybe do like 10 to 20 laps, various kind of things. But our goal was to have, at the time, people were using artificial beacons. You know, I worked in a General Motors factory before grad school where robots were following cables buried in the floor. And in fact, my sort of grad school personal statement was motivated by, why do we have to rip apart a big expensive car factory to pour concrete with wires carefully buried in the floor for the robots to follow? The robots should be able to navigate like people. They should be able to use the geometry of the world. And Hugh had the same inspiration. And really, the goal was to use, we called it geometric beacons, to try to use the geometry of the world to guide us in a way that lighthouses might guide someone sailing at sea. And coupled with that, trying to build the map. So this is for sort of taking data very painstakingly from moving a robot by hand, because it was sort of too much dead reckoning error to try to do it live, and taking sonar observations and trying to kind of combine them from different vantage points. And so they're extracting features and then matching them either to extract, say, plane features or corner features, and dealing with multi-reflections and different things. So that's kind of some of what I did as a student. This is actually part of Hugh's office. I stole part of his office. I used it in the middle of the night one day. I just said, let's just make a very simple scene. So we did more complicated scenes, but sometimes I actually think like going back to the basics. That's why, for example, you know, I'm going to talk later about using playing cards as very simple objects. I think sometimes if you go back to the basic simple problems, they can shed light on the path forward, and then you take it out in the ocean. You do something, you know, in a much more complicated environment. But this basic idea of incremental map making, we have a robot, let's say either we know its initial position, or maybe there's a little uncertainty relative to the initial reference frame. The robot observes some objects in the world. There's uncertainty in those observations. The robot moves. The robot takes, when it moves, there's uncertainty in its motion. You know, Rod Brooks said, robots take error-laden readings. They try to move a certain distance and direction. They do so only approximately. The robot reobserves, say, the first two objects, observes a new object. This actual PowerPoint slide, I think, is 20 years old. It might have been Paul Newman or Jose Neras or one of my early students, or I might have made it. I don't even remember. I've been showing this kind of thing. I'm going back to like the historical thinking about, like, we have some objects in the world, we have a sensor or a robot that moves. Embedded in this sort of simple formulation, as we scale up, as we increase the complexity of objects, you know, we have you know, this kind of fusion process of combining data. At least for Gaussian representations, this was kind of understood, you know, back in the 80s. But you know, and we can think about, you know, the inference problem, the maximum likelihood estimates of the robot and the object or landmark locations, given all the measurements. But the real world is not Gaussian. And so if we want to deal with objects, we can use approximations, but is there a way that we can get beyond the Gaussian assumption and still have real-time performance? So I'll come back to that. Let me just say a little bit of history. I know Andrew Davison spoke, and I quickly zoomed through his talk. I don't know if he showed this one. I didn't see it. Andy kindly shared this with me. This is the first real-time visual SLAM implementation, to my knowledge. This is in the Tom building of Oxford, the tallest and ugliest building in Oxford, the engineering building. Andy used a real-time active vision stereo head to be able to navigate around the lab, tracking and extracting visual features, reobserving them. And so just, you know, vision just suddenly becomes maybe possible. And in a historical survey, I do want to give a shout out to Juan Domingo Tardos and Jose Nira, two dear friends who really, with the SP map formulation and then the joint compatibility branch and bound algorithm, really thought deeply about consistency and data association and kind of like leading the way. So I wish I could talk like another 20 minutes here about SLAM history and acknowledging lots of friends and early contributions. I think a few key things that I picked out. So if you go back to the representation state estimate sort of autonomy, when in the mid 90s, the SICK laser scanner came onto the scene. I wonder if I don't have a SICK laser scanner in my office, but I've got a Velodyne over there. But anyway, I always viewed the world in this more object-based view of the world. But Lou and Milius presented the idea of pose graph optimization, where you change your representation and you have just the poses with the raw laser data. And this really lended itself to the SICK laser scanner, where you could correlate laser scanners. So here you can see back and forth in a corridor with dead reckoning error. Can we do correlation of the laser scans to correct for that error? And this was a really important sort of historical kind of changing into representation, thinking a little more focused on the robot pose and a little less on the objects in the world. And building on this, for example, Gutmann and Kotelnich had one of the first effective loop closing algorithms where they could go incrementally around a loop and then do a correlation with like kind of larger scale scan matching to close loops. And so around this time, kind of the late 90s, early 2000s, this big kind of wave of interest came with the convergence of some just really energetic researchers. And I was fortunate we had the first SLAM summer school, so 19 years ago in Stockholm. Truly, truly wonderful experience. This is Hugh. This is Wolfram Burgard, who I think I met there for the first time, a dear friend. Juan Domingo Tardos, Michael Montemelo, who leads mapping at Waymo, the Google self-driving car project. I think one way of thinking about it is if you could have invested in SLAM almost as a stock 20 years ago, like I believe all the people in this picture, most particularly Sebastian Thrun, it was the impact of these people is just tremendous. And if you think, when I think back, I have this picture of Hugh and Sebastian arguing about, sort of Kalman filters versus particle filters, just that sense of like passion and excitement. And, it's just such a privilege to be part of this community. And I think that, but I think clearly, so I was really excited to see a Tartan SLAM series. So the history of the original SLAM series, 2002, Stockholm, 2004, Toulouse, 2006, Oxford, 2009, Australia, and everyone said, oh, SLAM is solved. We don't need any more SLAM summer schools, and which is probably a verbatim quote from one of my colleagues. But I actually believe that there's still plenty of great work to be done. And so if I look back on the talks you've had so far with Sebastian and Michael and Mike Milford, Andy Davison, Paul Huang, Luca Carlone, watch all of their talks. And I would I believe in everything, like all of their kind of passion and all of the sort of potential research problems. I think, for myself, I almost see like the union of all of the ideas expressed as things that I'm interested in. Still to this day, I get excited when I read a SLAM PhD thesis. I just feel that, anyway, so I was going to try to say a little bit more about what we're working on in my group, and then some open problems. So let's see. So, okay, so if with that sort of context, I think that there still is work to be done in inference and representation for spatial AI. And so we're working on semantic representations that can enable robustness and efficiency. And I think this age-old problem, going back to Maravik, where am I? What are the objects around me? This heartbreakingly difficult problem. One of the things that my hero, Rodney Brooks, often said is, look at the assumptions that folks are making and try to challenge or break those assumptions and see what happens. And I think if we go back to the issue of representing uncertainty with Gaussians, either implicitly or explicitly, we will have situations, especially in sparse environments, ambiguous environments, where we have to deal with multiple modes of uncertainty. So partly inspired by the constraints of COVID, going back to like very simple problems, we said, can we work on this problem of multimodal or non-Gaussian inference? So in this kind of back to the basics world, what are the approaches to try to be able to handle multiple modes? And another really influential colleague, Tomás Lozano Perez, I'm looking for the book on my shelf. Tomás, whose office is right above mine now, he wrote a foreword for a book 30 years ago for Ingemar Cox edited for autonomous robot navigation and mapping. And he said, we need to develop, he said, the developing methods to take a robot from point A to point B is deceptively hard. And he said, he suggested we need methods that can postpone irreversible decisions. And I think, can we create sort of ambiguity tolerant robots that can handle multiple modes? A lot of our algorithms tend to do well when things are relatively unimodal, and they'll make some hard decisions about data association, but then that makes them kind of brittle, and can they recover? So if I go back to the underwater context, and this is a slide from my student Kevin, if you think about 1 and 2 long-term semantic mapping, maybe you're mapping coral reefs, or you're surveying some underwater environment. You know, imagine with no GPS, LiDAR is not going to work, limited data communication, sparse environment, potentially dynamic, and obviously a high cost of failure. That kind of motivates us to think about the semantic SLAM problem, where we try to combine objects and locations and data association decisions into a joint kind of inference problem. And so if you have time, I'll point you back to Kevin's ICRA 2020 paper, which formulates this max mixtures approach, so if you've seen Michael Case's presentation, Michael did a wonderful job of showing that for even a simple SLAM scenario, because of that interplay between pose uncertainty and object feature uncertainty with data association, small scenarios can quickly lead to a number of hypotheses that are greater than the number of atoms in the known universe. So under the hood, there's this potential tremendous computational complexity. But one of the things we believe is that nature is not out to get you. There's a lot of situations whereby, you know, every single what if hypothesis does not need to be entertained. But in general, you just need the ability to entertain relatively small number of ambiguities. And so let's see. So the hypothesis set grows exponentially, as Michael eloquently described. And so we're going into a regime of approximate inference. And my former student Ed Olson had an RSS paper at, I think it was Sydney 2012, on max mixtures, where you try to take a mixture of Gaussians and represent the overall distribution by the maximum of those, which would have some appealing sort of computational properties. And so partly inspired by that work, and you know, this is just a quick reference to some other literature. So the max mixtures work, definitely the Sunderhoff's various contributions looking at robustness, switchable constraints, etc. You know, we're heavily influenced by Atanisov Bauman's work on semantic SLAM, the MHISM2 that Michael talked about. We're effectively, let me go back. Michael talked to you about the history of factor graphs in SLAM. And so in this pose graph representation, factor graphs truly are kind of a language or a machinery for doing the kind of SLAM inference. And so what we are doing is taking like a foundation from GTSAM and trying to add in different types of factors that can help represent these mixture representations. So Kevin's 10-minute ICRA 2020 YouTube talk is online, and I'd say insert Kevin's talk here if you want more detail. But the quick kind of summary is we want to represent, this is with a kind of kitty example, we want to be able to either take measurements and associate them to new landmarks or known landmarks, and have represent some ambiguity with respect to, focus here primarily on multiple modes of pose uncertainty for the robot, but that based on different data association possibilities, we get multiple hypotheses for the robot pose. So we have an implicit representation for handling multiple hypotheses that's akin to the max mixtures that permits you to use, my PowerPoint has started playing automatically, I'm not sure why, that lets you use GTSAM and explore this sort of multi-mode sort of situation. So just a quick little example of our ICRA 2020 work, did a test in MIT's buildings 3, 5, 7 off the Infinite Corridor using April tags as a proxy for objects with multiple object classes based on the identity of the tag, kind of modular arithmetic, and inserting artificial 10% misclassification rate and adding some ominometry error. So a scenario of comparing with known data association, maximum likelihood, and then the different max mixtures for this kind of navigating around in a loop and showing how the approach handles the ambiguities that are encountered when you come back around the loop, compared against the max likelihood solution. And let's see, why is sorry about that. I'm not sure what my PowerPoint's acting up a little bit. Okay, so let's see, so it's 12:48. I do need to take questions soon, right? So the new work I want to point you to, and I'm happy to give another talk in the future, if anyone's work with Zichi and Chad and Kevin in our lab that's recently accepted to IROS 21, which builds on this for an ambiguity-aware object-based navigation scenario. And during COVID, I had this idea. We had students truly stuck in their dorms and apartments. How can we be experimental roboticists? And so I was actually playing cards a lot with my wife during COVID every night after dinner. And I said, we should just be able to use playing cards as objects. And in particular, if you think about an object that has a symmetry, so for example, the 8 of clubs, that if the robot sees it from one direction or sees it from the other direction, now you could create a specific object class that represents that sort of mod 180 kind of ambiguity. But I'm curious in situations where either through like multiple copies of the same card or seeing one card from different angles, that you can sort of expose some of the issues of the brittleness that comes from the unimodal assumption. Or put another way, can we kind of make an artificially designed test case where we can break existing algorithms that make the Gaussian assumption and try to overcome that? So just briefly, I'm going to give you the sort of quick run through. And this is a more general problem, not just for 2D objects. So with coffee mugs, if you have an object with a handle and you can't see the handle, you're obviously going to have some uncertainty in the pose. There's been some great work at a few other places looking at pose uncertainty, for example, one out of Google. And let me maybe perhaps use this slide to give you the sort of overview, and then I'll kind of pause and say some thoughts on the future and ask questions. The traditional representation of a lot of SLAM has evolved towards a front-end, back-end distinction, where we have back-end techniques like GTSAM, G2O, SESync that do the map estimation given the loop closures or associations to features. And then the front end is more about extracting features, data association, maybe loop closures. But traditional backends will fail if they're given too much ambiguous information from the front end. What we'd like to do is to try to create a better connection between the front end and the back end with contributions in both places, where we can try to do multi-hypothesis kind of pose estimation, say for objects, and have a back end that is more tolerant or aware of ambiguities. And so this work is an example. So let me just, apologies here, I'm just gonna, for time, gonna kind of jump to the punchline here. If you can, so the technique effectively does a reinitialization of landmarks to handle ambiguity. So if you think of this down here, shows versus for this, we did a little experiment with a race car or a small robot, a Z camera observing and a black fly camera observing features. And just to give you the idea here, so there's a machine vision detector, kind of a feature-based detector that can detect different playing cards. A ground truth, we did this in the mocap upstairs in the holodeck at CCL just to have a ground truth trajectory. And comparing here a single hypothesis versus a max mixtures representation. And as it's, perhaps you're saying we're sort of setting up a little unfair test, but basically the robot's kind of mowing the lawn going around, but when it reaches the point where it's coming back and it reobserves a feature, so say like right here, as it's like reobserving a feature that it saw from one direction from the other direction, its assumptions are verified. Say this would happen to be the jack of clubs. And this is how the single hypothesis solution kind of blows up. With the max mixtures representation coupled with this dynamic reinitialization, the algorithm has an ability to effectively do kind of mode switching and sort of as it unfolds in time to choose, say, wait a second, I should follow that other mode. And to try to just give a little more expressive kind of versatility rather than getting baked in to a single hypothesis. So I skipped all the details for that. I'm sorry. I do want to show you our paper. Let's see the archive. 1 second. I have is here. So our paper's just put on archive if you want to know more of the details. And then I'm gonna wrap up. So just a few more. Okay. So just a couple more thoughts. So the summary of that is we have this. We're trying to add a pose ambiguity awareness in object-based SLAM, where we take the max mixer's ability to keep track of multiple pose hypotheses, couple it with a reinitialization procedure that tries to track the correct modes. And more generally on inference, I point you to David Rosen's work, SE-Sync, and David has some great talks online. In general, a lot of SLAM has been in this fingers crossed kind of regime where if we're in places where there are good global minimum, we're okay, but this kind of handling multiple local minima, how do we create robustness? We wrote a recent survey paper that's also on archive, trying to survey the kind of just the last few years, the recent papers in these areas of inference and representation. And let's see, 1252. I'm going to give you my sort of the future part. So if I'd said a lot of past, a little bit of present, and then some future sort of topics for discussion. My view is that robust semantic SLAM, the ability to move around the world with objects, maybe have those objects move, maybe is really not just an engineering problem. I actually think there are fundamental new tools that we need to create. I feel like the library of objects that we have available for semantic SLAM is too small. I've seen some great recent research on kind of components, but to be honest, I've not seen a really compelling implementation that is sort of generalizable and maybe sort of self-learning can sort of help us. We need the robot to do some of the hard work for us. I think dynamic environments really break the assumptions of a lot of our models, and we need new ways of thinking about very long-term operation. And what would it take to match the sort of elegance and robustness of biological systems? And I also believe that we need to strive towards a shared autonomy with people, say robots helping older folks in their homes. I think that one of the other benefits of a more semantic understanding of the world is you might be able to connect that to language and connect that to people. So in conclusion, I remain optimistic for basic university research in this problem. I think that there's truly great work to be done. I think where am I and what is where in the environment, they're really kind of timeless research questions. I would say when Rodney Brooks said much remains to be done to produce complete solutions in 1986, I think that is still true today, at least in very challenging environments. And what are the representation and inference techniques to enable this robust long-term autonomy? Can we enable self-learning for robots? For example, objects move in the environment. Can robots exploit that and sort of kind of learn about objects through motion in the world? Machine learning is obviously critical as a tool, but I don't feel that end-to-end learning with canned data sets is necessarily going to take us there. The kitty data set is not going to lead us alone to autonomous navigation. And I think human-robot interaction based on these symbolic representations is important. Okay, so I'm going to stop there for Q&A, and thank you so much for your attention.
John, thank you very much. This was really great to span the whole area from the history to future and including some of the current work. We have a number of questions here from the audience, and we're trying to place this in some order. I guess one question here that actually, so one thing I wanted to say, I think it's actually, I really like the idea of going back to 2D, to simpler problems, basically to simplify the problems so that you can focus on the actual, how to solve that problem, rather than, we have found that, so building a 3D object-based SLAM system is actually incredibly hard and in some way distracts from the fundamental problems that underlie, the robustness that we actually want to solve. So here are a number of questions from the audience. So do you think that we will ever end up discovering a computationally tractable way of doing probabilistic inference with non-Gaussian noise? If so, do you see any promising directions that can be taken from a fundamental standpoint?
Great question. So we have another recent paper that I was tempted to talk about, which by no means answers that question, but it's called normalizing flow ISAM. And but the normalizing flows are techniques to sort of map arbitrary distributions into Gaussians. And I think that, and it uses some machine learning techniques to do that mapping. And more generally, I was involved in some work completely unrelated to robots, where folks are using machine learning for really solving partial differential equations, like really hard problems in fluid mechanics and related fields. And it may be that machine learning will enable the sort of multi-hypothesis, sort of non-Gaussian inference. There will be machine learning under the hood that kind of does the inference for us. For example, the work of Youssef Marzouk at MIT, and I can point you to others. But that's a great question. So I actually think machine learning might help us do the kind of inference that we wanted to do versus a sort of black box end to end.
Okay, great. Another question from audience here is, as the adaptation of learning techniques rises in SLAM, how can we give more robust, provable correctness guarantees as opposed to empirical evaluation that machine learning systems rely on? This becomes especially important as SLAM gets deployed on safety critical systems such as self-driving cars.
That's a great question. I'd point you to sort of David Rosen's SC Sting work with Luca and Afonso Bandera as an example of trying to think about how techniques, for example, from using duality and convex optimization, that it's not always going to be possible, but for the situations where an algorithm can self-certify its solution, I think here's a very sort of loose colloquial way of thinking about it. It's one thing to know something; it's another thing to know that you know something. So how do we have systems that can almost kind of certify, for example, that they have a trajectory estimate that they can certify, or they can say, you know what, I don't have a trajectory estimate I can certify. I better stop, ask for help from a human. But that's a great question, and I believe that coupling into some of these other communities, that there's some great math, and I think it has strong applicability to what we care about.
Krishna has a live question.
Hi, John. It's good to see you.
Hi.
Yeah, I was wondering if you had thoughts on, like, a lot of your talk was about representation learning, and do you have thoughts on, like, coupling representation learning with the downstream tasks that these representations are being used for? Because not all tasks require the same kind of high fidelity or dense representation. So yeah.
I think that's a great question. I think here's a conjecture. Are you better off to try to have a system, like, say you had a robot that did a particular manipulation task, that it might try to learn representations that applied to that task with lots and lots of training data and lots of testing and evaluation, versus is there more of a generic underlying machinery that you could almost pre-endow all robots with, so that there'd be sort of an emergent understanding of geometry to be able to do some manipulation tasks. So I think I guess I would I know that the trend in papers, and then sort of like the great work out of Berkeley with all learning from manipulation, the trend is that machine learning based in a more blind way on data seems like it's going to win. But I have this kind of gut feeling that there's something more of in terms of a more generic understanding of geometry that could enable a much broader applicability. Can we learn geometry? Can we apply learning to know about geometry and then use that? Does that make sense?
Yeah, thanks.
Right, another question from the audience. A lot of SLAM systems are developed for planar motion of the robots. However, if we speak of robots manipulating objects, say in a household or hospital, what should be the objectives of such a SLAM system, and what are the challenges in realizing them?
That's a great question. I think increasingly my students are using the terms like on-manifold kind of inference and learning, and I think that really getting beyond sort of a planar or Euclidean kind of view, but more thinking about how do we we're doing these challenging inference problems on complex manifolds, I guess. So I think you know, it's that was my initial. When I heard planar, we got to go beyond planar. Let's get on manifold. As like almost, there was a recent paper I saw from Hong Kong, I think, on manifold Kalman filtering that sort of has this more general kind of framework and view and that sort of captures some, say, what Paul Huang's work on MSc EKF with Sturgis Riemann-Liotis. So I feel like you know, for that broader class, I think there's some tools out there for math. But when you mention like hospital environments, I'm worried about things like clutter. Like, how does the robot avoid like pulling a cable out of the wall and turning off the pace, you know, the breathing machine or something? Like the just complexity and clutter of hospitals and houses and homes with pets and furniture and all kinds of things that can fall over and fall down the stairs. I think that beyond like the math of, you know, the inference problem, there's just dealing with the complexity and clutter of the world. You know, how do we, that's really hard.
Another question here is, in the world of SLAM, what role does infrastructure like GPS play? Do you think GPS is necessary for robust navigation, or rather redundancy that can be overcome with better visual SLAM methods, especially when it comes to multi-agent or swarm behavior?
Sure. Well, in some ways, I used to joke that, so when I moved to MIT in '91, I actually couldn't find a job. So I had sent out applications to various labs. And there was this kind of feeling in the early '90s that GPS was going to solve robot navigation. And but because GPS doesn't work underwater, I would joke and say, like, I have a job because GPS doesn't work underwater. But it turns out that, you know, with things like the urban canyon effect and just for needs of greater precision than GPS can deliver, that you know, there's this, you know, broader applicability of these tools. I think if GPS is available, it would be silly not to use it in an application. But I think that it is. I would again put you to Sunderhoff's work, great work on like doing outlier rejection for GPS and related things. It's actually non-trivial to use GPS. For example, I had a student, Jacques Liederkirchen, worked on with Mars, working on the mapping at the Charles River from a surface vehicle. And when he went under a bridge, the GPS signals, it's not that they disappeared, but they were multipath signals. So you kind of need to know when to trust the GPS, when not to trust the GPS. And he developed a kind of classifier. And so it's one thing for a sensor just to not give you any data. But the problem is, and we see this underwater with multipath, is it gives you a reading that's actually wrong, but you can't easily know that it's wrong. So another thing happening in my lab is we're doing some work with ultra wideband ranging with the DACA UWB modules. And those are really hard to model the errors because they'll miss the direct path and, you know, and so anyway, I think the short version is don't trust GPS too much, but use it if you're in a domain where it works well.
Oh, and a live question by Akash.
Hi, hey John. So I had a question which was more related towards like normalizing flow SAM and like trying to basically get machine learning to work with test time optimization sort of methods, right? So a lot of like SLAM kind of relies on having learning which you do in sort of a streaming way. Like, how do you think, or like how would you think we would be able to like marry these machine learning sort of like methods with SLAM, right? So effectively, like with normalizing flows, like what you're doing is you're trying to learn these sensor models of sorts for like specific sensors. Like, do you think there are like other ways to do this, get test time optimization working for machine learning models?
Sure. Well, a few things. So when you mentioned like streaming, that's like, I've had this inspiration of I would call it robot, a long-lived robot that dreams every night. So imagine a robot that navigates around Stata for 3 or 4 hours. We plug it in and then it recharges its battery. But while it's recharging its battery, it's kind of like reprocessing its data. And I'm thinking of some of the work for like the normalizing flows for like learning these mappings of different. And so imagine if the robot, like every day when it wakes up, it's actually used this kind of offline learning techniques to improve its ability on the next day to kind of make sense of the world around it. And so is there an interplay between this sort of online real-time streaming and the kind of offline batch consolidation? And one way of thinking about a problem like SLAM is it's almost like a compression problem. It's like one representation is just all of the data you've ever taken, which is obviously too much. So how do you decide, how do you compress that? And actually, I think people talk about the memory problem when I talk to biologists, like how do you remember things? But I almost think the hard part is not the remembering, it's deciding what to forget. And how do you, for example, it's very easy to have a system that if it operates for a very long time, it might actually, there's one object in the world and it might actually make 3 or 4 or 5 different copies of that object because it doesn't quite know. And so this, how do you sort of do the consolidation of the map representation to say, oh, this is actually the same thing I saw yesterday, remove it from there, or even in a single session, like, oh, this and this were actually the same object. So this doesn't necessarily go back to training for the normalizing flows, but just the general philosophy of there's what the robot does in real time to kind of survive its day and perform its tasks, which maybe those are a little more sloppy or a little more loose, but then can it use a sort of robot dreaming phase to consolidate its representations, tune its inference engines, and do better the next day?
That sounds like, yeah, that sounds interesting. Yeah.
Thanks.
Thank you.
So, and there's a follow-up question to the GPS from before. So we are now reaching a point where HD maps are grabbing a lot of attention. Do you think this engineering brute force to essentially turn a SLAM problem to just localization based on a known map is a good and sustainable path for autonomous driving industry?
Sure. Well, for autonomous driving, and just a disclosure, I'm a technical advisor at Toyota, and I think I certainly see the virtue of maps, and I think the challenge is how you keep them up to date, how you maintain them, and know if it's wrong. I think that maybe I feel like history will be the judge, but you can look at obviously the Tesla approach, which is based on massive kind of fallback, or at least massive deployment via over-the-air updates of code out to these set of beta testers and users, versus say a Waymo approach, which is more carefully engineered of having very precise maps in a limited area. I think that the future might see some sort of blending of the two, where you get more kind of, I guess, here's what I would say. I'm gonna turn this question back to the question about sort of certifiability and trustworthiness of answers. Is that if you need a human to actually check the result of the map and say, either when you're making the map, the historical legend is that someone at Google used to be the person who blessed every map before they used it. And it was only one person had that responsibility and authority. And so if you're gonna turn many robots autonomously loose in the world, is it feasible that humans could say the map's correct before the robot uses it? And that a human could tell the robot if the map's no longer up to date? Those are really hard questions. But I do think that HD maps can be useful, and that can be created and can be useful.
Good. Here's another good question from the audience. The majority of bio-inspired SLAM systems are topological or semi-topological. Are there any issues to build object-based SLAM systems with grid cells and place cells models?
Well, I have a grant from the Navy to try to do that from the Office of Naval Research, the Neuroautonomy Project at Boston University, and Michael Milford's a collaborator. And in some ways, I'm kind of on the hook to try to do that. I would love to do that, more bio-inspired object-based. And in some ways, it's kind of what we're trying to do. But what I would say, so obviously there's so much how the brain works, the deep mystery, huge fields of neuroscience. We're building across the street, the Brain and Cognitive Science Department. I'll tell you one little story. I recently got I checked out a neuroscience book from the MIT library, and because the library is closed, they mailed it to my house. It's a big, thick book. And the very last chapter in the latest edition of the book is about grid cells and place cells and memory. And so for whatever reason, the understanding right now through like patients like HM with the hippocampus is that if the hippocampus and its coupling to the entorhinal cortex with grid cells and place cells, that mechanism for positioning is essential to forming long-term memories. So my view, I've had this vision of like robot Google, where a robot could sort of almost be like a search engine for the physical world and keep track of what's where in the world. And what is the kind of indexing mechanism where you can know how to sort of what to remember, how to remember it. And my just completely unscientific kind of, is like the grid cells and place cells and that sort of metrical machinery that is almost a sort of scaffolding or a sort of a tagging mechanism or an indexing mechanism that then allows longer term memories to be performed. And so, but the brain we know has object, kind of what pathways and where pathways. The entorhinal cortex has different parts about objects and about places or poses, and they interplay with each other to form memories. And so, even though most bio-inspired systems have been sort of topological, and I'm a huge fan of Mike's work, Mike Wilford's, and what might be plausible, I actually have a very almost like extremely strong view that we have a subconscious metrical kind of machinery almost at work that we have this innate ability to know about geometry and location, and that it would be, having had that ability, it'd be crazy for the brain not to use that in some way for memory formation, place recognition, path integration, etc.
Great. Maybe this is a good ending point here also, since we went quite over time and took much more of the time than planned. No, sorry for having so many questions beyond the time. So yeah, thank you very much again,